Hello everyone. In last lecture we have talked about the relative stability, and in this lecture let's explore more about this. Okay, so in last lecture we have seen that when the poles are located far away from j omega axis in LHF of S plane, or that y axis we can say, the response decays to 0 much faster as compared to the poles close to the j omega axis. So the conclusion of that discussion was, the more the poles are located far away from the j omega axis, the more the system relatively stable. Okay, and for that we have to see the Routh stability criteria or a test. Now for that we have considered one example, one comparison, response comparison, inside which we have taken two systems, system A and system B, as a response. So here if you see, this is your y axis denoting the response or output, and this is the x axis denoting the time. Okay, now if you carefully see this, this dotted line shows you the system B response, and whatever the continuous response that you are watching over here, that is system A response. Now after comparison of these two responses, we can say that system A response decays slowly. Okay, means in other words we can say that its settling time is more and it takes more time to it takes more time to set to the output or desired output. Comparatively, if you see the system B, its response decays faster, or settling time is small, we can say, and that's why we can say, although both systems are stable, but relatively talking about the relative stability, or relatively B is more stable than A. So this is the example that we have seen. Okay, now let's see this graph as well. Okay, so here you can see the locations of poles and its comparison. Okay, so here if you see the system A complex conjugate poles, so if you see these are the system A poles we can say, and these are the system B poles. Okay, so from watching or comparing this graph or response of a poles, then we can say that system B is more stable or relatively more stable than system A. Okay, because these poles are system B's poles are far away from this j omega axis. Okay, and if you see here, these are near to this j omega axis, so that's why although it is stable, it is relatively less stable than the system B. Okay, so that was the discussion that we have done in last lecture. Okay, now we have to see one interesting thing, that is Routh stability criteria, and that is very important to decide, or while deciding the stability of any system, and that is very easy to understand. Okay, so let's see that. This also the conclusion that we have to see, that is relative stability improves as one moves away from this j omega axis. Okay, so that is the conclusion, and that is the basic things you have to keep in your mind. Now let's move towards the most important point inside that stability point, that is Routh stability criteria. So for a transfer function, Cs by Rs is given by b0 s raised to m plus b1 s raised to m minus 1 plus up to bm, divided by a0 s raised to n plus a1 s raised to minus s raised to n minus 1 up to this a raised to n. Okay, now here we have to clearly observe this denominator. Okay, so in this criteria the coefficients of denominator are arranged in array, and that is called as Routh's array. Okay, so what we have to do is that whatever the transfer function is given, just see that transfer function, see the coefficients named as a0, a1, a2 like this, and these coefficients are arranged in array which can be called as Routh's array. Okay, and this equation can be denoted like this, which can be also called as a characteristics equation that we have seen already. Okay, so this a0 into s raised to n plus a1 into s raised to n minus 1 plus up to an is equal to 0. This is your characteristics equation, and out of that we have to find out the coefficients like this a0, a1, and like up to a1, and we have to adjust this in an array. And how to adjust that, let's see. Sorry. So see here, the coefficients of s raised to n and s raised to n minus 1 row are directly written from the given equation. Okay, now here before studying that array, we have to see the basics about that. Okay, so if you see this, the name given to the array, row of the array, that is s raised to n, s raised to n minus 1, then s raised to n minus 2, then s raised to n minus 3, and up to s raised to 0. Okay, now this is the Routh's array that is shown over here. Okay, and see carefully how it is adjusted. This is your characteristic equation that we have discussed earlier, that is a0 into s raised to n plus a1 into s raised to n minus 1 up to an is equal to 0. Now the coefficients are like this: a0, a1, a2 up to an, like this. Okay, and as discussed earlier, the rows are s raised to n, s raised to n minus 1, n up to s raised to 0, based upon the equation that that is given by the examiner, we can say. Okay, so now see here, first what we have to do is that for s raised to n, that is the first row, and for the second row, that is s raised to n minus 1, we have to directly write the coefficient from the equation. Okay, now here if you see the coefficients are named as even coefficients, we can say, that is a0, a2, a4, a6. Okay, and these are written in a first row, that is s raised to n, and if you see the second row, that is s raised to n minus 1, odd coefficients are written over here, that is a1, a3, a5, a7, like this. Okay, now these two steps are very simple and very important, because based upon these two steps or these two coefficients only, the next things will be calculated. So carefully observe this odd and even coefficients, and again I am repeating, in the first row, that is ascend row, s raised to n row, we have to write down even coefficients a0, a2, a4, a6, like this. Okay, and in next row, that is s raised to n minus 1, we have to write odd coefficients like a1, a3, a5, and a7. But see how the notation is given, it is starting from a0. Okay, so this is called as e1, a2 is called as e1, a4 is called as e1. Okay, don't see the number, see the coefficient. Okay, so that's why the first is a0, that you have to keep in mind. Okay, so I think this is clear to you. So this is a0, a2, a4, a6, that is first row. Second row is a1, a3, a5, and a7. Now the next procedure, see carefully, because that is again very important, and that will decide your the different coefficients inside the Routh's array, and that coefficients ultimately will decide the stability of the system. Okay, so the first thing that you have to do is that carefully write this, and the calculation of this equation or coefficients is very important. Okay, so what we have to do is that for the next row, that is s raised to n minus 2, this first coefficient we have to calculate, and for this first coefficient, see how the multiplication is done over here. Here a1 into a2 means what? This and this, it is multiplied, minus this a3 into a0 divided by this a1. Okay, see carefully again, this a1 and a2 minus a3 and a0 divided by a1 is taken over here in this equation. Okay, so whatever the coefficient that is above to this, the calculating coefficient, we can say, or the coefficient that we are going to calculate, about that is divided here over here. And if you see this 4 coefficient over here, the cross multiplied, and they are just what we can say, the minus is taken over here. Okay, so a1 and a2 is taken, and minus a3 into a0 is taken, divided by the coefficient about this, that is a1. Okay, I think you got this. So again, what we have to do for that b2, let's see. Again, see carefully, now we have again taken this first elements of this, or first coefficient of these two rows into consideration. Okay, but here what we have taken, this a1 into a4, see carefully, a1 into a4 minus a5 into a0, or a0 into a5, divided by, again a1 is taken. Okay, see carefully, again a1 is taken, a3 is not taken. Okay, because whatever the first element is taken, whatever the first element is considered for the b1 calculation, that same element is considered over here. Okay, so here if you see the equation again, a1 into a4 minus a0 into a5 divided by A1. Okay, so this is all about the B2. Now I think you can easily calculate about B3. Let's see for that. Again, see B3, this first elements are considered every time, that you have to keep in mind, and A1 is divided for that also keep in mind, and this cross multiplication is done and minus is taken. Okay, so like this. So here this A1 into A6 minus A0 into A7. Okay, so that you have to keep in mind, divided by this A1. Okay, so this is all about this B1, B2, B3. Okay, now we can't take B4 because there is no any next column to that, and we cannot consider, because as we go on increasing this rows, these elements will become less. Okay, you will understand this in upcoming slides. Now see here, the other things we have calculated now. Now the same technique is used for the next row, that is S raised to n minus 3 row, but only previous two rows are used. Okay, that is S raised to n minus 1 and S raised to n minus 2. Okay, that you have to keep in mind. Okay, now what we have to do is that we have to calculate the elements for, or coefficients for the next row, that is for S raised to n minus 3, and that is denoted by C1. Now again, it is very easy to understand, same procedure we have to follow, but just above that two rows are considered. Okay, means what, for B1 we are considering S raised to n and S raised to n minus 1, and for C1 we have to consider S raised to minus 1 and S raised to n minus 1 and S raised to n minus 2. Okay, now here C1 is equal to, again it is very simple to understand, that is B1 into A3 minus A1 into B2, or B2 into A1, divided by B1. Okay, and I think you understood this, and you can easily calculate C2, and that also you have to understand that there will not be any C3 in this. Okay, because the elements will be less as we go on calculating this. Okay, that I have discussed earlier. Now the C2 is, again, if you see, I think it is not visible to you, that B1. Okay, so let me show that. Okay, so here if you see, C2 is equal to, again we can say B1 into A5 minus B3 into A1. Okay, divided by B1. Okay, so I think up to this it is clear now. Okay, now the next thing that we have to do is that we have to see how this is arranged, and what is the basics behind this. If you see this, each column will reduce by 1 as we move down the array, that we have discussed earlier. Okay, but for if you see these first two rows, because we have calculated from that, or we have written over there with the help of that equation, so that's why the elements are same over here. But as we go on calculating that, the meaning is that as we go on calculating that, this one element will be reduced as we go on increasing the rows. So here each column will reduce by 1 as we move down the array. Okay, now this process is obtained till last row is obtained. Okay, so see, this is very important. This process is carried out till last row is obtained. That is very important, that you have to keep in mind. Okay, don't left this in between. Okay, because we have to complete this process, then only we can easily understand and clearly and correctly understand the stability of that system. So this process is carried out or obtained till last row is obtained. That is very important thing. Now, okay, now this is all about the mathematics that we have done earlier. Now we have to apply that Routh's criteria. Carefully see this. This is very important slide. See here, the necessary and sufficient conditions for a system to be stable is all terms in the first column at the Routh's array should have same sign. See carefully, again I am reading this. The necessary and sufficient condition for a system to be stable is all terms in the first column at the Routh's array should have the same sign. Okay, and there should not be any sign change in the first column. See carefully, whatever it may be, positive sign or negative sign, all the signs should be same. If there is any sign change, then we cannot say that the system is a stable. Okay, so here must have the same sign, whatever it may be, positive or negative. Okay, but that sign must be same. Let's explore more about this. See, when there are sign changes in the first column of Routh's array, then the system is unstable. Okay, now here see, this A0 is positive, this A1 is positive again. Up to this it is okay. Okay, we are not interested in positive or negative, we are just interested in sign changes. But if you see this third row's first element, it is minus B1. Okay, see carefully, the sign is changed over here. Again this minus is changed to the plus in the fourth array, fourth row, first element. Okay, so here plus A0 plus A1, up to this it is no problem, it is correct. But here it is changed from negative, changed to negative from positive, and again from negative it is changed to the positive. Okay, now we can say that when there is sign change in the first column of the Routh's array, then the system is unstable. That is clear now. And there are roots in RHP. Okay, so why this is happening? Because the roots will be in RHP. Due to that it is happening. Okay, so that we can conclude about this. And number of sign changes equals the number of roots in RHP. Okay, so if there are two sign changes, then there will be two roots in RHP. If there is only one sign change, we can say there is only one root in RHP. Okay, so the number of sign changes equals the number of roots in RHP. So here easily you can observe there are two sign changes here. This first one from positive to negative, and here second one that is from negative to positive. Okay, so that's why this Routh's criteria is very famous and extensively used for deciding the stability of a system. Okay, in industries or in at the applications wherever the control systems are used. Okay, so that's why this is very important, which requires less time to decide the stability. And along with stability as well, it is showing you the number of roots in RHP. Okay, so that is again very important thing which is getting from this Routh's criterion. Okay, so I think you got about this Routh's criteria, and I think we have to see now the examples. Okay, so up to this I think it is very clear to you and you can easily understand what we have done. Let's have a look on that, what we have done, so that we can easily solve the examples. Okay, so we have started from this Routh's stability criteria, and that is very important. So we have to just take the transfer function and just take the denominator equation. Okay, why denominator? Because denominator is characteristic equation that we have discussed earlier, and that is very important, and from that we are getting the coefficients like A0, A1. Okay, now here we have to adjust the first two rows, the first row even elements and second row odd elements or odd coefficients from this characteristic equations, that is A0, A2, A4, A5, sorry, A0, A2, A4, A6, A1, A3, A5, A7, like this, and we have to calculate the elements like this. Okay, so that B1 is equal to A1 into A2 minus A3 into A0 divided by A1, like this we have to go on. We have to calculate this, and what we have to do is that we have to calculate this rows up to the we can say last element, that is for only one element may be remaining at last, I think, and up to that we have to do this, and except this first two rows, the elements will be decreased by 1 in next upcoming rows that we have seen. Okay, and finally we have seen that there must not be any sign change. Okay, we are not interested in positive or negative, whatever it may be, but there must not be any sign change. If there is sign change, then no doubt system will be unstable, and that number of sign changes will give you the number of roots in RHP, that is right hand side of that S plane. Okay, now let's move towards the example. That is example number 1, that is s raised to 3 plus 6s raised to 2 plus 12s plus 8 is equal to 0. Now here they have given directly your characteristic equation, and they have not given a transfer function. Sometimes they will give a transfer function, and just we have to consider that denominator and we have to equate to that 0, and from that we can find the A0, A1, A2 and A3. carefully see, don't confuse here, don't start from A1, okay, because we have to start from A0. That you have to keep in mind, because sometimes you may make this mistake, okay, in future. So that's why I'm telling this, start from A0, A1, A2, A3. okay, so here S3's coefficient is A0 and here it is 1. Here S square's coefficient is 6. Here S coefficient is 12, that is A2, and here the last coefficient is A3. okay, so here it is S raised to 0. I think you know this, S raised to 0, S raised to 1, S raised to 2, and S raised to 3, like this. So here in short, A0 is 1, A1 is 6, A2 is 12, and A3 is 8. Now first we have to do is that we have to take the A0 and A2, that's even elements or even coefficients. So A1 and A0, that is 1, and A2, that is 12, that we have taken. Secondary we have to do is that we have to take the S2, okay, row. This is all about the S3. Now we have to take S raised to 3. Here we have to take about the S raised to 2. okay, so here for S2 or S square, we can say we have to take this A1 and A3 elements, okay, because these are the odd elements. So 6 odd number elements, okay, odd number elements, that you have to keep in mind, 6 and that is 8. okay, now here we have to calculate B1, we have to calculate B2, and after that we have to calculate this AN. okay, so let's calculate this. So B1 is equal to what? A1 into A2 means what? This into this minus A3 into A0 means what? This into this divided by A1, that is 6. So here the calculation will become like this, that is 6 into 12 means this into this minus 8 into 1 divided by 6. okay, now if you do this calculation, this will be 72 minus 8 divided by 6 will be there. okay, so finally you will get the value like this, that is 10 into 67. Now here we have to add the zeros here because we have to calculate B2 over here. okay, so we can't directly write only B1 over here because S0 will be there, that you have to keep in mind. okay, if that will be, this is a S0 or S raised to 0 we can say, then it will be end over here, but it is started from S raised to 3 row, S raised to 2 row, and here this is S raised to 1 and it is that is S raised to 0. so that's why that will be last element, so that's why it is mandatory to calculate B2, that you have to keep in mind. okay, so it is not completed over here. okay, this thing you have to keep in mind. okay, sometimes some terms may be missing, that we will see in upcoming examples, don't worry about that. okay, so let's see the calculation of a B2. okay, now let's see how to calculate this B2. Now this B2 will be what? 6 into 0 minus 1 into 0 divided by this 6. okay, don't confuse over here, don't take this 8 as denominator over here. okay, so this B2 will be 6 into 0 minus 1 into 0. so whatever is, the result will be there, 0 minus 0 will be there. okay, and I think it will be 0. yeah, it will be 0. Now we have to calculate this, we can say AN over here. okay, so here we have to do next calculations, that is 10 into 67 into 8 minus 6 into 0 divided by 10 into 67. okay, so that will be there. So here finally we will get the 8 over here. okay, so that is the last element, okay, that we have seen. okay, now see this first column. okay, so the elements are 1, 6, 10 into 67 and 8. Now if you observe this 8, that is S0's coefficient, and these are the same. okay, we will talk more about this. okay, we will explore more about this in upcoming examples, but for time being just ignore this, just see the stability of the system. okay, now here you see, if you this first column, there is no any sign change, so all the elements are positive. So that's why I can say that as all the elements in first column are the same or are of same sign, hence this system is a stable. Okay, so it is shown over here, the elements in the first column are of a same sign. Okay, so I think you got this. So these are the elements that we have got. This first row is 1, 12, 0, second is 6, 8, 0. See, this 0 and 0 we have taken extra for calculation of this below elements that we have seen. Then if you see this third row, that is 10.67 and 0, and that is last element, that is 8. Okay, so I think you got this, and we have to stop here. In next lecture we will see more examples. Okay, so for today this must be sufficient, and thank you very much. We will meet in next lecture. Thank you.